Hi, welcome to another video. So in the previous lecture we discussed that the absence of autocorrelation is one of the fundamental assumptions which have to be fulfilled in order to end up with the reliable output of the OLS model. So in this video we are going to discuss some causes for autocorrelation, how to detect autocorrelation, and how to fix that bias. So first of all, a quick reminder, autocorrelation occurs when the disturbance term associated with one observation is affected by the value of disturbance term associated with another observation, typically one of the previous observations. Symbolically, we can say that covariance between error term in period I and error term in period J, or error term associated with observation XY and error term associated with observation XJ is not equal to 0. So we can deal with both the positive and negative autocorrelation, and positive autocorrelation occurs when higher value of error term in period T is associated with the higher value of error term in period T plus 1. Negative autocorrelation occurs when higher value of error term in period T is associated with the lower value of error term in period T plus 1. For instance, on this graph, you can find the example of positive autocorrelation. So here, the value of error term is affected positively by the value of error term associated with the observation in the previous period. Okay, so there are several fundamental causes for autocorrelation, and one of them is that some variables are lagged. So change in the value of regressor independent variable in period T affects the regressant or dependent variable in period T plus 1. So in this case, serial autocorrelation is really likely to occur. So for instance, you can think about the effect of education on productivity of employees, or even better, spending on education and training of employees and their productivity. Even if you start to spend more money from company budget on education and training in year 2022, you will only see some results in period 2024 probably, because people need some time to get trained and educated, they need some time to adjust, and so on and so forth. So here it just arises from the nature of processes you analyze. You have to be aware of this, and you have to consider this when designing your regression model. Another possible reason is inertia. So some economic processes are cyclical, and some of those are characterized by inertia. For instance, during the period of economic recovery, increase in the level of GDP is associated with increase in the level of GDP in the previous period. I mean, we are here at this fragment of the business cycle diagram. Also, the opposite is true for the period of recession. So GDP increases in this period, it decreased in the previous period, and so on. So, yeah, inertia. And another reason is seasonality. So you remember I told you during the previous lecture why it is always a good idea to use seasonally adjusted data for your analysis, and this is the reason. So sometimes variation occurs at some specific time intervals. So here we have quarterly GDP, and there is something known Christmas rally, and this is due to the fact that quarterly GDP is always the highest during the fourth quarter. So there is some very obvious reason behind this, because people spend more money before holidays, but also it's the end of accounting year for many firms, so they have to spend money from the budget and so on and so forth. So yeah, and that's why you have this process repeated every year. So every year GDP in quarter 4 is the highest, then it decreases to the lowest, and then it increases, and so on and so forth. So basically those small peaks on this diagram are just due to the seasonality. That's why it's always a good idea to adjust data for seasonality, because then you are less likely to end up with autocorrelation. And another possible reason for autocorrelation is non-stationarity. So in stationary data, mean or expected value and variance of the dataset do not change over time. And basically, stationarity serves as the very basic assumption for time series data analysis. So most of techniques will not work unless data is stationary. In contrast, in non-stationary data, mean and variance change over time. So non-stationarity can occur because of unit root or deterministic trend. That's why it's always useful to check your data for the presence of unit root. And again, you can run this test in Gretel if you click on the variable and choose testing for unit root. So here I analyze whether CPI or consumer price index trend is stationary or not. In this test, the null hypothesis states that unit root is present, and alternative hypothesis states that unit root is absent. And as you can see, based on p-value, we do not have sufficient evidence for rejecting the null hypothesis. In other words, we have to conclude that data is indeed non-stationary. However, there is some good news for you, and it is that it's relatively easy to handle unit root by transforming the variable to the first difference of the variable. So here, instead of CPI, I will analyze delta CPI, change of CPI between two periods, as you can see here. So now, as you can see, we can successfully manage to reject the null hypothesis in favor for the alternative hypothesis. So typically, when you have some problems with autocorrelation because of the presence of unit root, you can transform your data to the first difference. Finally, you can use Gretel for running some formal tests in order to detect whether there is autocorrelation bias in your model. First of all, Durbin-Watson statistic is the very basic one. You can find it in the output for any model. And theoretically, if there is no autocorrelation, its value should be equal to 2. If it is higher than 2, then there is negative autocorrelation. If it's lower than 2, then there is positive autocorrelation. In this case, as you can see, it's significantly lower, so I have to conclude my model is biased by first order positive autocorrelation. So yeah, Durbin-Watson statistic is only for the first order autocorrelation. So you can check whether error term is affected by the value of error term in the previous period, but this is like maximum capacity of this test. You can go for the alternative, which is a Brush-Godfrey test for autocorrelation. You can choose the order, like by how many periods you are going to analyze the presence of autocorrelation. So here, for instance, I analyze whether error term in period t is affected by the value of error term in period t minus 1, t minus 2, t minus 3, and so on up to period t minus 12. So in this test, the null hypothesis states that there is no autocorrelation, and yeah, we will also reject it in this case. So there is definitely autocorrelation in the first and the second, and for some reason in the fifth period. Okay, so that was it when it comes to detecting and handling autocorrelation. Hope it was useful, and see you in the next video.